Chapter 13, Chemical Equilibrium. Our outline is the equilibrium constant K and the equilibrium expression, homogeneous and heterogeneous equilibria, Kp, ice tables, reaction quotient, and Le Chatelier's principle. The equilibrium constant and equilibrium expression. Let's consider the reaction 2NO2 forming N2O4. The NO2 is a dark brown color. In fact, it's the dark brown of typical air pollution. And N2O4 is colorless. If we put brown NO2 in a sealed flask, it lightens as it forms some N2O4, and then the color remains. It doesn't go completely colorless, but the lighter brown color remains. On the other hand, if we put colorless N2O4 in a flask, it darkens a bit. It doesn't go totally dark brown, but it does darken a bit. Then the color remains. In fact, the color would be the same regardless of whether we started with brown NO2 and it lightened, or colorless N2O4 and it darkened, as long as we don't change the conditions. The reaction in either direction doesn't go to completion. What we call an equilibrium, a steady state, is achieved somewhere between all NO2 and all N2O4. Some reactions don't go all the way to completion, and these would be referred to as equilibrium reactions. So, let's say we're back to putting the NO2 in a flask. It reacts quickly. Remember from the kinetics chapter, when we have a lot of it, which is when we first put it in the flask, it reacts the quickest. The reaction slows down as the concentration of NO2 decreases until the NO2 concentration becomes constant. And that's when the color persists. As N2O4 forms, it eventually begins to reform NO2, and the rate increases as more NO2 forms until the N2O4 concentration becomes constant, and the color persists. When the concentration becomes constant, equilibrium is obtained. That's what we call equilibrium. It's in chemical equilibrium. So if we look at the diagrams A, B, C, and D, then we see initially there's just 10 molecules of NO2. The O is represented by the red balls and the nitrogen by the blue ball. So they're in the flask, and then some N2O4 forms. That's shown in diagram B, down in the third row. After more time has passed, then more N2O4 is formed. In fact, we have 3 molecules of N2O4 and 4 molecules of NO2. As more time has passed, we're now in diagram D. Notice we still have 3 molecules of N2O4 and 4 molecules of NO2. We would say that equilibrium has been achieved in diagrams C and D and any time beyond, provided we don't change the conditions. But notice that where those N2O4 molecules are in C is not the same as where they are in D, because although the amount of N2O4 is constant and the amount of NO2 is constant, there is constantly NO2s combining, forming N2O4, N2O4 breaking down to two NO2s. It's what we call a dynamic equilibrium. There's a graph of concentration versus time, concentration on the y-axis, time on the x-axis. Notice that we started with NO2, so we have that. Its concentration decreases as time goes on. The N2O4, we had none to start with, but its concentration increases as time goes on until they become a constant amount. Notice the amount of NO2 is not equal to the amount of N2O4, but the amount of NO2 is constant, the amount of N2O4 is constant. Equilibrium is achieved as soon as that constant amount is present. To keep concentrations constant, the rate of the reaction in the forward direction, the forward reaction, must equal the rate of the reaction in the reverse direction. If they weren't equal, then we would be getting more of the NO2 or more of the N2O4, and its concentration would not be constant. So we could say equilibrium is achieved when concentrations are constant, or equilibrium is achieved when the rate in the forward direction is equal to the rate in the reverse direction. And we see that on this next graph, rate versus time. So we have rate on the y-axis, time on the x-axis, and we start with the NO2, so we've got it. Its rate is decreasing as it gets used up, but then the N2O4 is forming, its amount is increasing, so its rate is steadily increasing until it reaches a constant amount. We have two other graphs, and they are for the reaction of H2O plus CO in equilibrium with CO2 plus H2. By the way, we could use a straight yield sign to go from reactants to products, or if it's an equilibrium reaction and we are showing those equilibrium symbolisms, we could use that as well, which is a forward arrow above a reverse arrow. So we have the first graph, concentration versus time, and the second graph is reaction rate versus time. And we start with the reactants, and that's the green, and so their concentration is decreasing with time, but it reaches a steady amount. And the products form, they're represented by the red line, and we start with none, but they do react, they form, so their amount, their concentration increases, and they reach a steady amount. At that point, equilibrium is achieved. Or we could get the same information as far as when is equilibrium achieved from the reaction rate versus time graph. So the forward reaction, represented here by the red line, the reverse reaction represented by the blue line, and equilibrium is achieved when the rates are equal to each other. Alrighty, so back to the 2NO2 in equilibrium with N2O4 reaction. This reaction goes by elementary steps. Remember what that means from our kinetics chapter. An elementary step is one that goes exactly as it's written. So the forward reaction is 2NO2 reacting. That is, two NO2s have to come together to react. So if we were to write the rate law for the forward reaction, we would write rate of the forward reaction is equal to K, the rate constant for the forward reaction, times NO2 squared. It's second order because of the 2 in the stoichiometric coefficient 2 in the reaction. The reverse reaction, well, for that one, N2O4 is simply decomposing to the products, and it's not having to hit anything else, so it's first order because, again, I've told you that it's an elementary step, whether forward or reverse. So it's first order as the reverse reaction. So the rate of the reverse reaction, the rate law is rate equals the rate constant for the reverse reaction times the N2O4 concentration. At equilibrium, we have that the rate forward equals the rate reverse. And so we have rate F equals rate R, or KF being the rate constant in the forward direction. KF times NO2 squared equals KR times N2O4. We could also solve for the rate constants, that ratio. So we have KF over KR is equal to the N2O4 concentration over the NO2 concentration squared. Since KF and KR are constants at a constant temperature, remember they are rate constant, only temperature dependent, so if we keep that constant, they are constant, then their ratio is constant, and we set their ratio equal to a new constant that we'll call capital K, or K. Well, this also makes the N2O4 concentration over the NO2 concentration ratio, of course we have a square in there, constant at equilibrium. So we have KF over KR equals K, or K, the equilibrium constant, is equal to N2O4 concentration over NO2 concentration squared. This expression is the equilibrium expression, and K is the equilibrium constant. The equilibrium expression we write for each reaction, and it depends upon the stoichiometric coefficients in the reaction, and of course what the reactants are, what the products are. It's always products to their stoichiometric coefficient divided by reactants to their stoichiometric coefficients. K, the equilibrium constant, is temperature dependent, and we find its values in thermodynamic tables. So in general, if we have a reaction AA plus BB in equilibrium with CC plus DD, where the big case letters represent chemicals, small case, their stoichiometric coefficients, we would write the equilibrium expression as K equals C to the C power, D to the D power over A to the A power over B to the B power. Okay, so we will write the equilibrium expression for two reactions. They're all gases. Our first one is H2 plus Cl2 in equilibrium with 2 HCl. By the way, notice we say in equilibrium with when we have the equilibrium symbols, or we could simply say yields. Saying in equilibrium with is giving a little bit more information. Our equilibrium expression would be K equals HCl squared over H2 over Cl2, and by that, of course, I mean their concentrations in units of molarity usually. K equals, it turns out, I looked it up, 4.0 times 10 to the 31st at 300 degrees Celsius. By the way, K is unitless. Whether it is coming out that way or not, we always give it as a unitless quantity, simply a number. Here, K is very large, 10 to the 31st. This means that we have lots of HCl. We have very little H2 and Cl2. The reaction essentially goes to completion. A large K definitely favors products. Notice how it's written. We have products over reactants. A large K value means lots of products. Our next one that we will write the equilibrium expression for is F2 in equilibrium with 2F. So the equilibrium expression would be K equals F squared over F2. I looked up the value of K. At 500 degrees Celsius, it is 7.3 times 10 to the minus 13. That's a small quantity. That means we have very little F and lots of F2. F is not very stable. A small K favors reactants. Think about how fluorine exists when we have pure fluorine. It does not exist as fluorine the atom, exists as F2 the molecule. So we have very little fluorine. Had we written the reaction as, instead of F2 in equilibrium with 2F, 1/2 F2 in equilibrium with F, well, then we would have written K as K equals F over F2 to the 1/2 because of the 1/2 stoichiometric coefficient. This is the square root of our first K, which let's just for simplicity call K1, and let's call this K for the 1/2 F2 reaction K2. So we have that K2 is K1 to the 1/2, or the square root of K1. Well, K1 we have the value to be 7.3 times 10 to the minus 13. So K2 is 7.3 times 10 to the minus 13 to the 1/2, which is 8.5 times 10 to the minus 7. So make sure that you are comfortable with how to use the square root key on your calculator, and make sure that you would get that answer. Notice that K goes with the reaction as it's written. So depending on how the reaction is written, we can manipulate the value of K that we might find in a thermodynamic table to get the proper K for the reaction that we're actually working with it. Okay, our next problem is calculate the fluorine concentration at equilibrium, where F in square brackets, that corresponds to the equilibrium concentration of F. If we had written F naught or F sub I, then we mean the initial concentration of the fluorine atom. So if we simply have a chemical with the square brackets around it, we mean its concentration at equilibrium. So calculate the fluorine concentration at equilibrium at 500 degrees Celsius if the F2 concentration, so instead of just F the atom there, F2. I see the 2 that's way over on the left side. I think that should have been there by the F in the square brackets, where we should have F2 equals 0.070 moles per liter. Alrighty, so we have our equilibrium expression, F2 in equilibrium with 2F. K is F squared over F2. We're going with the expression written that way, F2 in equilibrium with 2F. So our equilibrium expression is just a reflection of that, F squared over F2. We're after the fluorine concentration, so fluorine the atom equals the square root of K times F2. K from earlier is 7.3 times 10 to the minus 13 times 0.070, And we end up with the fluorine atom concentration at this 500 degrees Celsius at equilibrium being 2.3 times 10 to the minus 7 moles per liter. So although we don't include units for K, we do include units, of course, when we're referring to concentrations. Our next problem is calculate K at 500 degrees Celsius for the ammonia reaction that I have below. If N2 concentration is 0.00200 molar, H2 concentration is 0.0400 molar, and the NH3 concentration is 0.0000878 molar. So our equilibrium reaction is N2 plus 3H2 in equilibrium with 2NH3, and these are all gases. So our expression is K equals NH3 squared over N2 over H2 cubed. We put in our concentrations given. We square, we cube, and so forth as needed. And we get K equals to 0.0602. Notice that K, the equilibrium constant, is a constant, only dependent on the temperature. So as long as we're working at 500 degrees Celsius with this reaction, we are going to have K equals to 0.0602. Even if we had a different equilibrium, a different set of equilibrium concentrations for those reactants and products, we would still have at 500 degrees Celsius for that reaction, K come out to be, at least within experimental error, 0.0602. Okay, so far what we have gone over is systems go to equilibrium spontaneously. Might take some time, it depends on the kinetics, but they will get to their equilibrium concentrations. And at equilibrium, we have the rate of the forward reaction equal to the rate of the reverse reaction. And we have the concentrations of the reactants constant and the concentrations of the products constant. They're no longer changing. For a given reaction, K is constant at a given temperature, no matter what initial reactant concentrations or initial products concentrations we might start with. K is only dependent on temperature. Our next section is homogeneous and heterogeneous equilibria. So in our reaction we just looked at, N2 plus 3H2 in equilibrium with 2NH3, we were told that those are all gases. That's what we would refer to as a homogeneous equilibria. They're all in the same phase. In fact, they're all gases in this case. This next equilibrium, nickel solid plus 4CO gas in equilibrium with NiCO4 gas, that would be a heterogeneous equilibrium because we have a mixture of phases. We might think the equilibrium expression would be, for that equilibrium, K equals NiCO4 divided by Ni divided by CO to the fourth power. It turns out that's not correct, though, in that the nickel ends up having a constant concentration, so we do not include it in our equilibrium expression. That is, let's say that we have a flask of nickel solid CO gas that we've put in, and it will then come to equilibrium with the product, the nickel CO4 product. Well, the amount of CO in our flask depends upon, the concentration of the CO in our flask depends upon the moles of it that we put into the flask and the volume of the flask. So we could put a lot of CO in and have a high concentration, or we could put not much CO in and have a low concentration. That is, that one has a variable concentration. But the solid nickel does not have a variable concentration. The concentration of the nickel in a chunk of nickel metal is independent of the moles there and like the volume of the flask. It's simply just temperature dependent. That is, if we are told the density of the nickel, and let's say we're told it to be 8.90 grams per ml, and you know how density just depends on temperature. It's a property of the solid that we can easily measure in the chem lab. We can convert from grams to moles using the molar mass. So we take that 8.90 grams per ml and we multiply by 1 mole over 58.70 grams, that is the molar mass. We see the grams cancel out, and now we have moles per ml. Well, if we want molarity, then we're going to convert the mLs into liters. So we multiply by 1,000 milliliters per liter. And now our remaining units are simply moles per liter, which would be molarity. So we can go from density 8.90 grams per ml to molarity, which we get 150 moles per liter. And that's just a constant. That is, as the nickel reacts, the amount of it, the mass of it, the moles of it decrease, but not its molarity. And what's in our equilibrium expression is molarity, not mass. So we leave the concentration of the nickel, which is constant, out of our equilibrium expressions. So K, the equilibrium constant and expression, would be K equals NiCO4 divided by CO to the 4th power. The concentrations of pure solids are not included in K because they're constant. The same is true of pure liquids. They are also not included in the equilibrium expression. So let's consider this example with water. H2O liquid in equilibrium with H2O gas. The equilibrium expression, we might think, would be the H2O gas divided by the H2O liquid concentration. But that's not correct, because while the H2O gas concentration in the flask varies depending on how many moles of gas we have and the volume of the flask, the concentration of the H2O that's a liquid is not going to change. It's a set amount that we could determine from its density. The density of water is about 1 gram per ml. We divide by the molar mass of water, multiply by the 1,000 mLs per liter. We get that the molarity at room temperature is about 55 moles per liter for water. That's constant, only dependent on temperature. So we leave it off of the equilibrium expression, and we have K is equal to simply the concentration of the H2O gas. And what we conclude here is concentrations of pure liquids and pure solids are not included in the equilibrium expression. We only include in our equilibrium expression concentrations that can vary. Okay, our next section is Kp, and we are going to get into that by looking at the N2 plus 3H2 in equilibrium with 2 NH3, which are all gases. Since these are all gases, it's easier to work with pressures than concentrations. K involves concentrations, moles per liter. We'll come up with an expression that involves atmospheres instead of concentrations. And the K for that, for when it involves atmospheres, we refer to as Kp, where P implies pressure. Okay, the connection between concentration, moles per liter, and pressure is PV is equal to nRT. So in our PV equals nRT, we have moles, N, we have liters, volume. So solving for moles per volume, N over V, we get N over V equals P over RT. Now let's look back at our equilibrium expression for this ammonia reaction. Since our reaction is N2 plus 3H2 in equilibrium with 2 NH3, the equilibrium expression involving concentrations would be K equals NH3 squared divided by N2 divided by H2 cubed. And instead of the square brackets representing molarity, we're going to put N over V to represent molarity. So we have N of ammonia over V squared divided by N of nitrogen over V divided by N of hydrogen over V cubed. Notice that although the N has to be specifying the chemicals, so we have N of ammonia, N of nitrogen, N of H2, the volume is the volume of the flask. So that's going to be the same throughout, so we don't have to have any specification for what volume we are referring to. Now, instead of N over V, we're going to replace that with P over RT. So we have P of ammonia over RT squared divided by P of nitrogen over RT divided by P of H2 over RT cubed. And we are going to pull out the RT terms. Notice RT is always a constant. T is just what is the temperature of the flask. They all have the same temperature. So the RT is the same RT no matter whether we're talking ammonia or nitrogen or hydrogen. So we're going to separate the pressures, which are in fact partial pressures, from the 1 over RT parts. So now we have the partial pressure of ammonia squared times 1 over RT squared divided by the partial pressure of nitrogen divided by the partial pressure of hydrogen cubed divided by 1 over RT divided by 1 over RT cubed, where we're going to call the ratio of the partial pressures Kp. So we have Kp equals P of NH3 squared over P of N2 over P of H2 cubed times 1 over RT squared times 1 over RT to the 4th. We have K equals Kp times RT to the 4th divided by RT squared, or K equals Kp times RT squared with just algebra to clean it up. Or solving for Kp, we have Kp equals K times RT to the minus 2. So in general, we have the relationship that compares K and Kp, where K equals, or rather Kp equals K times RT to the delta N, where delta N is the sum over the moles of the products minus the sum over the moles of the reactants. So we look at our equilibrium reaction and we add up the equilibrium, we add up the stoichiometric coefficients of the products, and we subtract from that the sum of the stoichiometric coefficients of the reactants. That is delta N. That is the exponent on RT, and that times K gives us Kp. So whether we're given K or Kp for a given equilibrium reaction, we can always calculate the other one. In our equation there, Kp equals K times RT to the delta N. R is the value 0.08206 liters per mole Kelvin. That is, it's the universal gas constant involving the moles and liters and atmospheres. And K is temperatures in Kelvin. Okay, here's a problem where we're working with Kp. What is Kp at 500 degrees Celsius for the ammonia reaction if the partial pressure of N2 at equilibrium is 1.20 atmospheres, partial pressure of H2 at equilibrium is 0.810 atmospheres, and the partial pressure of NH3 at equilibrium is 0.00309 atmospheres. We're also told that K, that is the K involving concentrations at 500 degrees Celsius, is 0.0602. So we have N2 plus 3H2 in equilibrium with 2 NH3, all gases. Kp is the pressure of NH3 squared over the pressure of N2 over the pressure of H2 cubed. We were given those pressures, so we put them in, squaring, cubing, and so forth. We get Kp is 1.50 times 10 to the minus 5. Notice it, just like K, has no units. We also could have found Kp from our expression Kp equals K times RT to the delta N, because we're given K in our problem. So we could have found it this way. Delta N, looking at our reaction, we have 2 NH3, no other products, so we take 2 and then minus the invisible 1 in front of the N2 and the 3 in front of the H2, so we have 2 minus the quantity 4, that is delta N is negative 2, so we have Kp equals K times RT to the negative 2. Kp is equal to 0.0602 times 0.08206 times the 773, which is the Kelvin for 500 degrees Celsius, that to the negative 2, and we get Kp is 1.50 times 10 to the minus 5. So to enter that in our calculator, we would type 0.0602 times parenthesis 0.08206 times 773 closed parenthesis caret negative 2. And Kp is unitless, as is K. Our next section is ice tables. At 600 degrees Celsius, a mixture of 0.500 moles of N2 and 0.800 moles of H2 is put into a 1.00 liter flask and allowed to reach and react and come to equilibrium. At equilibrium, it is found that the concentration of the N2 is 0.475 molar. From this information, calculate K. All right, so our reaction is N2 plus 3H2 in equilibrium with 2 NH3. They're all gases. The equilibrium expression, so we're after K, the one involving concentrations. K is equal to NH3 squared over N2 over H2 cubed. We know the initial concentrations and we know the concentration of N2 at equilibrium. What we're going to do in this problem and in many future equilibrium problems is set up an ICE table, an equilibrium table. So the N2 concentration, we are told it decreases from 0.500 molar to 0.475 molar. We see that the change is 0.025 molar. And we're going to represent that change with, for now, the symbol X. So the ICE table, what we do for ICE tables is we write out the reaction as if those are column headers in our table. And the rows in our table are where we get the term ICE. The initial row is the initial concentrations. So we have 0.500 for N2, 0.800 for H2, and 0 because there's no mention of it, so there must be none of it initially present. The second row is the change, C. That is the change in concentration. So the N2 concentration, it decreases, so we represent its change as negative X. The H2 concentration also decreases because it's a reactant, so it's going to be negative as well. But notice that 3 times it has to change. That is, we see from our reaction, if one amount of N2 changes, 3 amounts of H2 have to change. So the change there we're calling negative 3x. And the NH3, its concentration is going to increase, so we have the plus, or the lack of a plus there, but at least no minus. And because of the stoichiometry, we're putting a 2x there. The last row of our ICE table is the equilibrium concentration, so that's how we get ICE. For the N2, it is, we're told, 0.475. Now, the equilibrium concentration is the initial concentration plus the change. So for H2, it is the initial, 0.800, plus the change, so minus 3x. For the NH3, it's going to be the initial 0 plus 2x. Next, we have that we know what the X is because we can determine it from the information we're given about the nitrogen. So we have 0.475 equals, so the equilibrium equals I plus C, so 0.475 equals the initial 0.500 plus C, so minus X, or X is 0.025. So now if we replace the X in our table by 0.025, we have then negative 3x to be 3 times 0.025 or negative 0.075. And we have 2x to be 2 times 0.025 or 0.050. So then at equilibrium, we can know what the numbers are for all of our reactants and the product. So for the H2, we have 0.800 minus 0.075 or 0.725. And for the NH3, we have 0 plus 0.050 or simply 0.050. Now we have the concentrations at equilibrium, so we can put them into our equilibrium expression. We have the NH3, 0.050 squared over the N2 over 0.475 over the H2 cubed over 0.725 cubed, and we calculate K to be 0.014. At a given temperature, 0.108 moles of N2O4 is put into a 1.00 liter flask and allowed to react and come to equilibrium. We're told what the N2O4 concentration at equilibrium is. It is 0.060 molar. Calculate K. Okay, there's our reaction, N2O4 in equilibrium with 2 NO2, all gases. Our equilibrium expression is the NO2 squared over the N2O4. We set up the ice table as we did with our other problem. For the N2O4, we have a negative X for it. We have for the NO2 a positive 2X. Since we have the equilibrium value and the initial value for the N2O4, we can calculate what X would be. So we fill in our table with those values, and we have our equilibrium values for everything, and we put them into our equilibrium expression, and we determine K to be 0.15. So we have gone through this problem because it's very similar to the last one quickly, so come back and do it on your own at your own rate later. Here's a new problem. 3.00 moles of PCl5 is put into a 1 liter flask and reacts and reaches equilibrium. Calculate the PCl5 concentration, the PCl3 concentration, and the Cl2 concentration at equilibrium, given that K is 1.80 at whatever temperature we're working at. Our reaction is PCl5 in equilibrium with PCl3 plus Cl2. They're all gases, so they're all part of the equilibrium expression. Now, this problem differs from the last two in that we're given K and we're after equilibrium concentrations. What is known initially is different in this problem than the last one. Alrighty, so we start in the same manner. We write out our reaction, we make our ice table, we put in it what we know. We know we have 3.00 molar PCl5 to start with. We have no PCl3 or Cl2 because there was no mention of those in the beginning, so we put zeros. We put our X's, our negative X for the reactant because its amount is decreasing. Positive X for the two products. We have none of them to start with, so their value has to increase. It can't go down. So at equilibrium, we have 3.00 minus X for PCl5, X for PCl3, and X for Cl2. We write out our equilibrium expression, PCl3 times Cl2 divided by PCl5 equals K. We know K is 1.80. We put that in. We put in what we have for the equilibrium concentrations in terms of the X for the PCl3 the Cl2. And then for the PCl5, we have the 3.00 minus x. We do some algebra to get that to look like a quadratic equation. So, unfortunately, it's a little more complicated. It's a quadratic equation. So we have to use the quadratic equation solver. So we have x squared plus 1.80x minus 5.40 equals 0. Some of you might on your calculator have a quadratic equation solver program. If you don't, you can find one, do a Google search and type it into your calculator. If we don't want to do that, we can just use the typical quadratic equation method to solve it. So in general, we have ax squared plus bx plus c equals 0. And to solve for x, we have x equals minus b plus or minus the square root of b squared minus 4ac, all that over 2a. So we put in our value of b, negative 1.80. We put in our value of a, 1, c, negative 5.40, and we determine the values of x to be 1.59 or negative 3.39. Now, going back to our ICE table, we see that x is a positive quantity. It cannot be negative because the PCl3 and the Cl2 concentrations cannot go down. We have none to start with. So we know that x must be the positive root, not the negative root. It doesn't make physical sense. So x is 1.59. Going back to our ICE table, we see that PCl5 concentration at equilibrium is 3 minus x. We see that the PCl3 and the Cl2 concentrations are x. All right, so we have PCl5 equals 3.00 minus x, 3.00 minus 1.59, we get 1.41 molar. And then the PCl3 and the Cl2 concentrations are x, or 1.59 molar. So here's a problem rather similar to that last one we just did. Calculate the equilibrium composition, that is, the concentrations at equilibrium in a flask that initially held 0.800 molar N2 and 0.200 molar O2. K is 1.00 times 10 to the minus 5 at the 1200 degrees Celsius. The reaction is N2 plus O2 in equilibrium with 2NO, where they're all gases. So we write out our ICE table. N2, initial concentration 0.800. Its change is negative x. At equilibrium, we have 0.800 minus x. For O2, we have to start with initial 0.200. It changes by negative x. Equilibrium 0.200 minus x. For the NO, there was no mention of it, so there must be none to start with, so we have 0. It changes by 2x, the 2 because of the stoichiometric coefficient in front of the NO, 2. Positive because we have none to start with, so its quantity has to increase. All right, so at equilibrium for it, we have 2x. Our equilibrium expression is NO squared over N2 over O2. So putting in all of our terms, we have for K the 1.00 times 10 to the minus 5, which when I use equation editor, it's easier for me not to use scientific notation, so I wrote that as 0.00001. That equals 2x squared divided by 0.8 minus x divided by 0.2 minus x. So a little bit of algebra simplification gives 4x squared divided by 0.160 minus x plus x squared. More algebra finally gave us the expression 4 minus 0.00001 x squared plus 0.00001x minus 0.0000160 equals 0. So now we can use the quadratic equation solver. So we have what A is, we have what B is, we have what C is. And with a lot of carefulness in our attention to those tiny numbers and all the negatives and so on, we have x equals 6.31 times 10 to the minus 4, or x equals negative 6.34 times 10 to the minus 4. So we choose the positive root because we know that the NO2 concentration, that was our product where we had none to start with, cannot decrease. So x has to be a positive quantity. Going back to our ICE table, we see that the N2 concentration at equilibrium is 0.800 minus x. The O2 concentration at equilibrium is 0.200 minus x. And the NO concentration at equilibrium is 2x. So we apply those using our value of x, and we get that the N2 concentration is 0.799 molar, the O2 concentration is 0.199 molar, and the NO concentration is 1.26 times 10 to the minus 3 molar. That problem was kind of intense algebra-wise. Well, it turns out we could make the math a lot easier. Looking back at our ICE table, we have at equilibrium for N2 0.800 minus x. For O2, 0.200 minus x. Now, if the change, which is what x represents, is very tiny, perhaps x can be dropped with respect to the 0.8 and the 0.2, and that would make our algebra a whole lot simpler. Going back up here, we have k is 1.00 times 10 to the minus 5. K reflects how far the reaction goes to products. A very small k, and a k which is around 10 to the minus 5, is very small. A very small k implies the reaction does not go very far to products. The change, x, is very small. So if we could drop x with respect to those initial concentrations, it would make our algebra a whole lot simpler. And that's what I have in this paragraph here. Since x is small, the change in the concentration is small. That's what x represents. The reaction does not go far to products. This is because k is so small. In future calculations, if k is small, you can usually drop x with respect to the original concentration. We must, however, check this approximation. And the check is, if the x that we calculate in the end from the approximation is less than or equal to 5% of the smallest original concentration, the approximation to drop x with respect to the original concentration is okay. Alrighty, so when the math got pretty hairy, that's when we had our equilibrium expression. We have k equals 2x squared over 0.800 minus x over 0.200 minus x. That came about, remember, way back here when we had the equilibrium expression, we had these equilibrium terms. So we put those terms into our equilibrium expression. So that's where we're starting with on what we're starting with on this page. But we're saying let's drop x with respect to the 0.800 and the 0.200. Because whenever we're subtracting a number from another number, if the amount we're subtracting is really, really tiny, then it's probably insignificant. Now, of course, we can't drop the x in the 2x expression because when we multiply two numbers, whether one is big or small is going to have a big impact. But when we're subtracting, it might, or adding for that matter, it probably, if the amount we're adding or subtracting is very, very small, probably it's negligible. Okay, so with that approximation, we have 0.00001 equals 4x squared divided by 0.8 divided by 0.2, and the math is so much easier. We can very quickly get that 4x squared is equal to that tiny number. We can simply solve for x, which gives us 6.32 times 10 to the minus 4. Now, our check is we take x and we divide it by our concentration that we're dropping it with respect to. So we take 6.32 times 10 to the minus 4 and we divide by 0.200 times 100, and we get that is 0.3%, much less than 5%, so our approximation is deemed okay, and certainly the math is a whole lot easier. We would also check x with respect to the 0.8 that we dropped it with respect to, and we're going to get a number even smaller than 0.3. Alrighty, so now we finish up our problem. We have x, so we subtract that from 0.8 and get that the N2 concentration is 0.798 molar. The O2 concentration is 0.200 minus x, or 0.198 molar, and the NO concentration is 2x, or 1.26 times 10 to the minus 3 molar. Notice that those concentrations with this approximation are very similar to the concentrations where we went through the full math analysis. Alrighty, here's a problem for you to come back to. Concentrations of CO and H2 in a container are 0.37 molar and 0.72 molar respectively. At the temperature of the reaction, K is 0.0049, which is a rather small value of K. It's a 4.9 times 10 to the minus 3. What are the concentrations at equilibrium? There's what the reaction is, CO plus 2H2 in equilibrium with CH3OH. These are all gases. So we set up our ice table. We have our x's, negative x, negative 2x, x, and we go through, let's try dropping x with respect to those initial concentrations and check it later. So I'm going to have you go through this problem on your own at a later time. Make sure that you can run through it okay. Our next section is the reaction quotient, and A reminder, K is a quotient, it's a ratio, it's at equilibrium conditions, equilibrium. But sometimes we care about the quotient at initial conditions. This quantity we call the reaction quotient Q. So Q is just like K, except Q is at initial concentrations or initial pressures if we're dealing with QP. It lets us determine which way toward reactants or toward products a reaction will proceed. Okay, so far in all of the problems we have looked at, we have been given initially amounts of reactants. But sometimes instead we're given amounts of products, or maybe we're given that we initially have amounts of reactants and products. So what we have is, if we're given amounts of all reactants and products, we might not be able to just look at those and determine which way, whether to the forward direction or to the reverse direction, the reaction proceeds to achieve equilibrium. If we calculate the Q value and we compare Q to K, then we can know which way the reaction will go to achieve equilibrium. Alrighty, so in general, we have reactants forming products or reactants in equilibrium with products. Q would be the product's initial concentrations divided by the reactant initial concentrations. If Q is less than K, the reaction will proceed to the right. If Q is less than K, then that means that there's a lot of reactants and not much products. So the reaction will go toward products. If Q is greater than K, then what that means is there's a lot of products, not a lot of reactants, and the reaction will actually proceed toward reactants. If Q happens to be equal to K, then the reaction is already at equilibrium. Okay, so what we do is we're given a reaction where we're given amounts of all reactants and products. Well, we determine what K would be, and we compare it to, what Q would be, and we compare it to K. And then we know which way the reaction proceeds. So here's a diagram from your book that shows the direction the reaction shifts. When Q is less than K, it shifts to the right. When Q is greater than K, it shifts to the left. Another way to remember that is kind of think of it as a number line. If Q is less than K, we put it to the left side. If Q is greater than K, we put it to the right side of K. Now, Q will go to K. That is, the reaction will go to equilibrium. So, however it has to go, if Q has to go to the right to get to K, then we have the arrow to the right. If Q is on the right side of K, it gets to K by going to the left. That's a little sort of mnemonic that helps me. So here's an example where we would determine Q. So 0.120 moles of PCl5, 0.120 moles of PCl3, and 0.120 moles of Cl2 are put into a 1.00 liter flask. They react and reach equilibrium. Calculate the concentrations of everything at equilibrium where K is 1.80. So our equilibrium reaction is PCl5 in equilibrium with PCl3 plus Cl2. They're all gases. So since we have amounts of all reactants, we can't just initially know which way the reaction goes. If one of those were 0, we would know the reaction would have to go toward it. We'd be able to assign the plus and the minus x's. But if we have everything to start with, we can't just say right off. But we calculate Q, we compare Q to K, and we can know which direction the reaction goes. So Q is the concentration of the reactants, of the products. So PCl3, Cl2 over the reactant, PCl5, all at the initial concentrations. So we have the 0.120 times 0.120 divided by 0.120. We see that Q comes out to be 0.120. It is less than K, so that means the reaction proceeds to the right. So in making our ice table, we know that the reactant, PCl5, is the negative X, and the products are the positive values of X. So we fill in our ice table with our initial concentrations, our changes, so negative X, positive X, positive X, equilibrium values. We write out our equilibrium expression, PCl3 times Cl2 over PCl5. So then we have 1.80 equals 0.120 plus X times 0.120 plus X divided by 0.120 minus X. Now, in this case, we cannot drop X because K is big. K is not something like 10 to the minus 3, 10 to the minus 5, or smaller. It's 1.80. So we cannot drop X. Plus, if we dropped X, we'd have no X. So we have to run through all the math. We get 2 roots for X, 0.0944 and negative 2.13. Well, we know it's X is positive. We went through all the comparison of Q and K to determine that. So we drop the negative root. And so we find the PCl5 concentration at equilibrium is 0.120 minus 0.0944 or 0.026. The PCl3 concentration 0.120 plus 0.0944 or 0.214, and the same with the Cl2. So we went through that problem kind of quickly. Be sure to come back and go through it at your own rate. Our last section is Le Chatelier's principle. So we'll go through that by looking at the reaction involving ammonia. N2 plus 3H2 in equilibrium with 2NH3. They're all gases. This is called often the Haber process after a German chemist named Fritz Haber who worked with it. This reaction represents pretty much the main way that ammonia is made throughout the world. And ammonia is very important because of its use as fertilizer. And yet it's an equilibrium reaction. For the industrial production of ammonia, the equilibrium concentration of ammonia must be high enough to be economical. So how can the ammonia concentration be raised? And that's what Le Chatelier's principle works with. To change the ammonia concentrations, it turns out that we can add or remove substances. So we can change the concentrations. When we change concentrations, it turns out the value of K, the equilibrium constant, is unchanged. Remember, we've been saying throughout this chapter that K is only temperature dependent. It doesn't depend upon concentrations. We can change pressures by changing volumes. That also changes the equilibrium concentrations, but it does not change the value of K. We can change the temperature. Changing temperatures often will change the equilibrium concentrations as well as changing the value of K. So changing the temperature changes the value of K and changes the equilibrium concentrations, changing pressures, changing volumes, changing concentrations, initial concentrations, does not change the value of K. Only the concentrations at equilibrium change. So if we want to get more ammonia, as people who are making it industrially, if we want to get more ammonia, we can push the reaction toward the ammonia side by changing concentrations of N2, of H2, of NH3. We can squeeze the reaction flask down. That changes the amount of product we get. We can also change the temperature. That changes the amount of product we have. Of those three changes, changing concentration, changing volume, only changing temperature changes the numerical value of K. All three of those change the amount of product we get. We can predict how changing concentrations, changing volumes, and changing temperature affect the equilibrium positions using what's called Le Chatelier's principle. Le Chatelier's principle is if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction. It will shift to the left or to the right that tends to minimize that change. So what we have in this principle is we have a reaction at equilibrium. If we impose a change on it, the system tries to fight that change. It tries to minimize the effect of that change that we have imposed on it. That's what Le Chatelier's principle is. Okay, so now we will go through the three things we can change. The volume, the concentration change, and then the volume change, and then the temperature change. First, we will look at the concentration change. Okay, so the effect of adding or removing substances, that is changing the equilibrium concentrations. Once again, the numerical value for K is unchanged. K only changes its numerical value when we change temperature. Alrighty, so looking at the same reaction, N2 plus 3H2 in equilibrium with 2NH3, all gases, the Haber process. So let's say that we have that reaction at equilibrium, and let's say that our equilibrium values are given by that first row in the table. At equilibrium for N2, we have 0.399 molar. For H2, we have 1.197 molar. And for NH3, we have 0.202 molar. That's the equilibrium amounts. And then let's say that we impose a change on that by adding 1.00 molar N2. And we let the system come to equilibrium. Well, it tries to minimize the change in the N2. It does so by using up some of that N2. Of course, it has to use up some H2 as well, and it will make some NH3. What it will do to minimize the change we made is it will push the reaction to the right. And at equilibrium, after we've imposed that change, we find that the concentration of the N2 is 1.348, not 1.399. It's a little bit lower. The concentration of the H2 is 1.044. The concentration of the NH3 is 0.309. Notice that if you determine what K would be in our first equilibrium values and in our second set of equilibrium values, you would find that it's about the same value. K does not change the numerical value. So if we want to get more ammonia out of the process, what we can do is just add more N2. Or we can add more H2. That is, it will push the reaction to the right. Another way to get more ammonia is to pull off the ammonia as it's made. Le Chatelier's principle tells us if we pull off ammonia as it's made, the reaction is going to keep trying to make it in an effort to minimize that change. So industrially, ammonia is pulled off, removed as it forms, and that helps to drive the reaction to make more of it. All right, next we will talk about changing the pressure by changing the volume. So we have a reaction in a cylinder with a piston, and we can push down on the piston, we can pull up on the piston. So let's say that we're pushing down on the piston. The equilibrium responds to this decrease in volume, or we could say increase in pressure, by shifting the equilibrium in a direction that minimizes that pressure increase. So going back to our ammonia reaction, we have N2 plus 3 H2 in equilibrium with 2 NH3. Looking at the total number of moles of reactants, we have 4, 1 plus 3, compared with 2 moles of products. So if we have that ammonia reaction in a cylinder and we squeeze down, that increases the pressure, and what the system will do is it will go to the side with the fewer moles of gas. We will be in effect pushing it toward the ammonia side. And that is because the equilibrium expression for our ammonia reaction is N of ammonia over volume squared divided by N of nitrogen over volume divided by N of hydrogen over volume cubed. The volume is the same regardless of what gas we're talking about, so we pull the volume term out and we end up with K equals to N of ammonia squared divided by N of nitrogen divided by N of hydrogen cubed times V squared. We've decreased the volume, and yet the constant, the value of K has to be a constant. So if we decrease V, then that mole ratio must increase such that the mole ratio times V squared remains a constant value. So squeezing it down is going to make the N of the NH3 part increase. And so that's what we have done. And that's why by the equilibrium being pushed to the side with the fewer number of moles of gas when we decrease the volume in this reaction. The addition of an inert gas has no effect, as the volume, when we add an inert gas, the volume, at least ideal gas-wise, does not change. So industrially, the pressure is increased by decreasing the volume, and more ammonia is squeezed out. Industrially, this reaction is done at 250 atmospheres. So basically, look at the reaction that you're given and If the volume is decreased, the pressure is increased, it will go to the side with the fewer moles. If the volume is increased, therefore the pressure is decreased, it's going to go to the side with more moles. And all that's in an effort, Le Chatelier's principle tells us so, of the system to minimize that change. In a reaction with equal number of moles of reactant and products, changing the volume has no effect on the equilibrium since the volume component cancels out. Okay, so let's take a reaction of all gases, I2 plus H2 in equilibrium with 2HI. Well, we have 2 moles on each side. So if we look at the analysis as we did with the ammonia reaction, we see that the volume terms cancel out. So changing the volume has no effect on the mole ratio. So we would say squeezing, expanding, 2 moles on each side, it's not going to have any effect. Okay, now we look at our last effect, the effect of changing temperature. In this effect, the value, the numerical value of K is changed. Alrighty, so still looking at our ammonia reaction, it turns out it's an exothermic reaction. Heat is on the ammonia side. The reaction gives off heat, so does not favor being heated. Kind of like if we're hot, we don't want to walk into a hot room. In an exothermic reaction, so that is reactant A forming product B plus Q, heating the equilibrium system pushes it to the right. The numerical value of K decreases. Cooling this exothermic reaction, it's going to make it want to produce more heat. It's going to push it toward the heat side, and K increases. The numerical value of K increases. In an endothermic reaction, so we can represent that as A plus Q in equilibrium with B, heating it is going to push it toward the product side. The numerical value of K is going to increase. Cooling it is going to push it toward the reactant side. The numerical value of K is going to decrease. So just a big reminder, K is temperature dependent. So when we change volume, when we change concentrations, we have not changed the numerical value of K, only when we change the temperature. For our ammonia reaction, K is 3.6 times 10 to the 8th at a temperature of 25 degrees Celsius. So it goes far to products at 25 degrees, whereas K is 0.0602 at 500 degrees. And that's because it's an exothermic reaction. So when it's cool, it makes more product, it goes toward Q, but when it's hot, it goes away from Q. And you can see that reflected in the values of K. Higher yields of ammonia are obtained at 25 degrees Celsius, but the reaction is, unfortunately for chemists, too slow. The rate is approximately 0. Haber proposed to use a catalyst to speed up the rate. Bear in mind, the presence of catalyst does not affect the position at equilibrium. It does not make for more product. It does not drive the reaction left or right, since the catalyst increases the rates of both the forward and the reverse reactions. So Haber used high pressure to favor ammonia production and removed ammonia as it formed, and did so at low temperatures to have a high yield to have a large value of K, but used a catalyst to make it go at a decent rate. So lastly, we have this table to fill in. So we have a new reaction. We have 2NO2, that's the brown stuff, in equilibrium with colorless N2O4. That's an exothermic reaction. We see the plus Q on the product side. So what we'll do is fill in the first column of our table, the reaction response column. If we increase the amount of NO2, that will drive the reaction to the right. If we decrease the amount of NO2, that will drive the reaction to the left. If we increase the temperature, that will drive the reaction to the left. If we decrease the temperature, that will drive the reaction to the right. Our next column is Q. How does the value of Q change? So if we get a pencil and paper and write out what Q would look like. Q is the initial concentration of N2O4 divided by the initial concentration of NO2 squared. So if we have a larger amount of NO2, then that is going to decrease the value of Q because NO2 is in the denominator. If we increase the initial amount of NO2, we have decreased the value of Q. If we decrease the initial concentration of NO2, then that will increase Q. Q is not dependent on temperature at all. It's only dependent on initial concentrations of reactants and products. So increasing or decreasing T will cause no change to the value of Q. Our last column is how does K change with these changes? Well, K is the equilibrium concentration of N2O4 divided by equilibrium concentration of NO2 squared. K is only dependent on temperature. So increasing NO2, decreasing NO2, that will have no change in the value of K. But it is temperature dependent, so increasing, decreasing T will change the value of K. Since this reaction is exothermic, increasing T causes it to go toward reactant, and that will decrease the numerical value of K. Decreasing T will cause it to go toward product, and that is to increase the value of K. Whenever it goes more toward product by a temperature change, it means the value of K has gone up. Alrighty, well that's it for chapter 13. So go back through this video as it can help you. Definitely go back through the handout notes. Make sure that you can run through all of the examples we looked at. Read through chapter 13 in your textbook and do the assigned homework.